Hello, welcome back. So we've been talking about electromagnetic waves, which remember is just an oscillating electromagnetic field. It's just changing in time. And you know that as light. And so you also know that light reflects off of surfaces. So what we're going to look at today is how exactly does that happen? How does it reflect off the surface? Not only that, when something passes through, when that electromagnetic wave passes through an object, like for example glass or pyrex or acrylic or any kind of semi-transparent material, what we're going to find is that the light bends. And you've seen this before. If you've ever taken a glass of water or some kind of liquid and you take a straw and you put it in there, it's going to look like the straw is broken. What's actually happening is the light from inside the glass, from the straw, hits that glass and it bends. Your eye's not smart enough to trace that path back, so it just says, oh, well, it must have come from down here. And so the straw looks broken just because of that bending of light. So what we're going to look at today is why that happens, how that happens, and we'll actually do some calculations on it. Let's get started. Okay, so let's talk about reflection first. We have actually two different kinds of reflection, and just to be clear, we all know what we're talking about. If I have an object here that's not emitting light on its own, the only way that you can see it is if light reflects off of that and comes back into your eye from that. Now, if I have something coming off of a very smooth surface, a mirror, a polished floor, an apple, anything like that, then we call that specular reflection. And so basically the wave comes straight back to your eye. It's not getting spread out from that. On the other hand, if I have something that is hitting a coarse surface, and by that I mean lots of bumps, things like that, well, then there's lots of little places for it to reflect. And you can think of it as having lots of mirrors positioned in a lot of different angles. And so the light's going to get reflected out in a lot of different directions. And so that gives it a flat or a matte appearance to it. So we call that a diffuse reflection. So the pictures that we have here are something you may have experienced. On the left here, we have a wet road. Now, when the road is wet, then the surface obviously is going to be fairly shiny from that. And so we're going to get specular reflection. If you look at the headlights, the reflection of the headlights of the car are actually very bright. So they're coming straight back into your eyes. But notice that you can't really see the edges of the road. Remember, if the light doesn't bounce off of it, you can't see it. So this is why at night, when it's raining, it's very hard to see the road because you're not getting that reflection off of the edges of the road. All you're getting is just a reflection of any car lights coming straight towards you. Now, on the left here, we've got the same situation, but we've got a dry road. And this is an example of diffuse reflection. So the road is dry. So we've got this bumpy surface here. And you can see that we can now see the edges of the road. We can see more of the road surface is going to be lit up by the headlights here. Also notice that the headlights themselves are not so bright. Now that's for two reasons. One, that energy is not being reflected directly back into your eye. But two, think about conservation of energy. If I'm sending some of that energy off in all directions, not all of it's going to come back to my eye. And so it's not going to look as bright. So always keep in mind that objects don't emit their own light. Well, okay, based on temperature, we'll talk about that later. But in general, objects are not going to emit visible light unless it's a light bulb or something like that. The only way I can see it is if I've got some other light source hitting that and reflecting back. And so that positioning of the light source is going to be real important for what we're going to be talking about later. All right, so take a look at this next case here. And so as we said with microtask 1 here, the diffuse reflection is much dimmer, and that's simply because of conservation of energy. You've got a limited amount of energy, and all of it is not going straight back into your eye, and therefore it's going to be dimmer from that. Now, take a look at the apple here, the picture that we have right here. And you see these bright spots on the apple. That's the point where the light was directly hitting and directly coming back into your eye. So we call that a specular reflection. Now, all of the apple is being illuminated. So is being illuminated. So there certainly is some diffuse reflection here. However, the part of the curve of that apple that's going to be reflecting it directly back is going to be brighter from that. So this is what artists use to take a 2D piece of art. If you just draw a flat picture of an apple, it just looks like a red circle, right? But if you put this bit of specular highlighting on there, then all of a sudden your brain interprets that as being 3D because you're used to seeing this reflected spotlight coming back at you from that. So the other thing that we have to consider is that the white light that you get from the sun or from incandescent lights, things like that, actually contains all of the colors. And keep in mind that color is really just a perception in the brain, but so we can also say that it contains all of the wavelengths. But we traditionally associate different wavelength bands with particular colors. So there are 6 colors in white light: red, orange, yellow, green, blue, and purple. You may have to call that violet. That's also common. So those are the ones that are going to be strongest as they appear to your eye. Now, take a look at microtest 2. So white light is shining on the apple. What colors are being reflected from its surface and what are being absorbed by the surface? Pause the video and think about this, because this is going to be an important concept. Well, remember what we said, that the only time you can see something is if that light is reflected back into your eye. Since that apple appears red, then the apple must be reflecting only red light back into your eye. Only the red light is going back into your eye, which means all of the rest of the colors, orange, yellow, green, blue, purple, are actually being absorbed by the apple. And so that's maybe backwards from what you're used to thinking about. If you have a red apple, you're like, oh, look, it's absorbing all that red light. No, it's actually reflecting all of the red light and absorbing everything else. Okay, let's take a look at the picture down here at the bottom. And when you shine light on a mirror, that light is going to get reflected off of it. And it's a little bit easier to see if we're looking at a laser here, but this happens with just any kind of light, white light, whatever. Now, I'm sure you're aware that if I have light coming directly at the mirror, so at a perpendicular to the surface of the mirror, then it's going to get reflected right back out. And we know that we use the term normal to describe perpendicular. So it doesn't mean not weird. It means that it's at a 90-degree angle. However, if the light wave is coming in at some angle from that normal, and we can measure this one, call it theta 1, then it's going to come out at some other angle, theta 2. Right now, we're not sure how these two are related to each other. Now, I'm defining it right now relative to the surface of the mirror because that's kind of the most intuitive way to do it. What we're going to see in just a minute is that physicists usually are going to define things from this normal here. Because when you think about it, it makes sense, because if I have light coming in at that normal, it's going to come straight back out. So that's a good reference point for us to work with. And we'll address that in just a minute. Our derivations are going to be, for this problem, are going to be just a little bit easier if we do it from the surface. Okay, so let's see if we can figure out a relationship between this incoming angle 1 and this outgoing, this reflected angle 2. So here we've got that diagram at the top of the page here. It's very important that you follow along with the geometry here. And there's a reason, as we said, it's called geometric optics, because we do lots of geometry with this. And if you don't remember geometry from high school, that's fine. Mostly we're talking about right triangles. So let's see what we can figure out with this then. We'll switch back to our black pen. There we go. Actually, we'll use red. Okay, so here is our first wave. It's coming down this way, and then it comes down, it hits the mirror, and it bounces off. Now remember that it is not a particle. The whole wave doesn't bounce off, even though that's kind of what it looks like. It comes down here, and then you can think of it as lying flat. So the wave comes like this. But as this end is coming down, this end is going up. So it goes like that. And that's what's actually reflecting off of the surface. It's those wave emitters that are coming out. But we can think about it as being a beam. And so that's what we're going to do. I just don't want you to lose sight of what's really going on here. Okay, so take a look at microtest 4 then. How does the speed of the incoming wave front, and that's this one coming from B down to D, so it's this wave front coming down this way, how does it compare to the speed of the outgoing wave front? Got to be the same, right? They're all moving at the speed of light. So those obviously all have to be the same. Let me zoom out so we can keep seeing our picture here. All right, so how does the time for the right edge, that's that part at A, how that's traveling from, again, we'll go to red, that's traveling from here down to E. So from here to here, that whole length there, how does that compare to the time it takes the left edge to go from C to A? So think about what's happening. The wave has just touched at C. The wave here is at A, is still coming down. But as this one at A comes down and hits E, this one at C is moving up towards A. So how does the time it takes for this edge to go from here to here, how does that relate to the time it takes for this edge to go from here to here? Well, they've got to be straight. It's got to be a straight line all the way through. So if they were at different speeds, well, then that would curve as it went like that. So that means that the time required, red, has to be the same. So the time required for it to move for this end to reach here compared to this end to reach here must be the same. Okay, so given that the time is the same and they're moving at the same speed, what can you say about the distance from C to A compared to the distance from A to E? Well, this gets back to what you learned in the very first semester of the class. The velocity is the distance divided by time. So the distance is just going to be the velocity times time. If these two things are the same, well, then the distance has to be the same as well. Okay. All right, so how does the distance from B to D, so this distance we're talking about, I'll go back to my pen, the distance from B to D here, how does that compare to the distance from D to E? And we give you a hint. Let me erase some of my lines here so you can see it. We give you a hint that B is exactly at the midpoint of this line from C to A, and F is exactly at the midpoint of this line from A to E. So what can you say about those two lines? Well, they also have to be equal, right? So they have to be equal as well. Okay, so then how does the distance from C to B, here to here, compare to the distance from E to F? Well, we said that the distance from C to A was the same as the distance from A to E. Right? If you don't remember that, go back and kind of work through all the steps here. We're doing geometry, not physics, really. So, but B is at the halfway point. So if this distance is equal to this distance, half those distances also have to be the same. You're going to see why we're asking these questions here in just a second. So let's kind of sum up what we've decided here. We've decided that this side and this side must have the same length. We've also decided that this side and this side must have the same length. And the reason for that is basically because the speed of light is constant. So because the velocity can't change as it moves through there, then as it moves through the same medium, then those two sides have to be exactly the same. All right, so let's take a look on the next page, and I'm just going to slide this page over so that we can see both at the same time. Okay, so how does the angle CBD, that's this angle right here, compare to the angle DFE, that's this angle here? And we've given you a really strong clue with the symbol that we've drawn here. Well, because BD is perpendicular to CA, remember that's that line showing the wavefront coming in, and DF is perpendicular to AE, that's that line showing the propagation of the wave as it moves outward, also has to be perpendicular. Well, they're both 90 degrees. So since they're both 90 degrees, obviously they're the same. Okay, so now here's the geometry that you may or may not remember. If I have two sides that are the same, and I have an included angle that is the same, then there is a theorem that proves that these two triangles, this triangle and this triangle, must actually be identical. Okay? Don't worry about the proof of that theorem. If you're interested in it, you can Google it. But it does kind of make sense if you think about it. if this side is equal to this side and this side is equal to this side, and in this case it's a 90-degree angle, well, I could use the Pythagorean theorem, and you should see that you're going to get the same length for both of those, right? Because this side and this side are the same, or I'm sorry, this side and this side are the same, and this side and this side are the same. So Pythagorean theorem is going to give me the same no matter what. So that means that then that all of these angles have to correspond to each other. They all have to be equal as well. They're the same triangle. So that means then, think about it, this is flipped because this side is this side. So you can think about the triangle as kind of unfolding like this. So what can we say about this angle, this incoming angle, and the outgoing angle? They're going to have to be the same. Now, some students get confused and they want to say, well, wait a minute, Dr. K. If those two triangles are identical, doesn't it mean this angle and this angle are the same? No, because remember that this side is not equal to that side, right? That's what would have to happen for those two angles to be the same. Instead, this side is equal to this side, and this side is equal to this side. So that's what I mean by that kind of unfolding there. Make sure that you can visualize that. Okay, so given that then, those two angles must be the same. And that's what it looks like if you look at the picture that we drew. Here I had my mirror, and then I had the laser coming in this way, and then it got reflected off this way. This was that normal. It looked like those angles were the same. Just looking like is not enough. That's enough that it can give you a clue as to which direction you want to go to prove it, but we're going to have to use the geometry to actually prove it. So the incident angle then must be equal to the reflected angle. Now, as I mentioned a little while ago, there is one small wrinkle in that physicists traditionally define the incident angle to be from the normal and not from the surface. And the reflected angle will be from the normal and not from the surface. There's two reasons for that. One is that the fact that, if I have a light ray coming into the mirror directly normal, it's going to bounce straight out. So that's a good reference point. Second of all, when we start talking about refraction, or when it actually goes into the medium and bends, then it's going to always be from that normal. And so we may as well define these angles for reflection as well. So this is the law of reflection. And it's actually pretty obvious. The law of reflection simply says that the incident angle must equal the reflected angle. And it doesn't matter if I measure it from here and here versus here and here. Let's say that this was my theta 1 and this is my theta 2. Just like we said before, this is a right angle. So this angle must be 90 minus theta 2. And this is also a right angle. So this angle must be 90 minus theta 1. So if theta 1 is equal to theta 2, well then 90 minus theta 1 is equal to 90 minus theta 2. So no matter how you draw it, you're always going to get that these two angles are going to be the same. Right? So the incident angle is equal to the reflected angle. That's the law of reflection. That's something you should keep in mind. Okay, so using this, we mentioned that we call this geometric optics. It's also called ray optics because we're talking about having a ray of light. But that ray of light, remember, is nothing more than showing which direction the peaks of my light wave are propagating. But it's still useful because this makes it much cleaner when we're trying to do this kind of geometric proof that you see here, where we're trying to say, okay, I want to figure out this angle of incidence and this angle of reflection coming through. So we're going to be using that for pretty much the rest of the semester here. And I'm going to keep reminding you of this, though. Don't forget that it is not a light ray, even though we're calling it that. That light ray that's coming in is nothing more than showing you the direction those wavefronts are propagating through space. Okay. All right. So when we study Maxwell's equations, I'm going to go ahead and delete this page here. When we studied Maxwell's equations, we found that the speed of light was constant. And go back through your notes, see if you can give me an equation from Maxwell's equations that tells me the speed of the incoming wavefront. Well, in that case, it was light, and so C was that constant of integration, and it was mu 0 epsilon naught. And since those were determined by constants of the universe, if I am in vacuum, if I'm just out in space, then that's a constant. However, one thing we didn't mention was the fact that when this electromagnetic wave is propagating through some other medium, other than just going out through empty space, it's actually going to slow down. And if you think about it, that makes sense, right? If I have air, for example, let's pretend that I've got sound in air, and then I want to try to send sound through water. Well, that water is a denser medium. And so the sound waves, the speed of the sound in the water is going to be slower than it's going to be in air, just because the sound waves now, instead of having to vibrate air molecules, I'm trying to vibrate water molecules to come through that. And those water molecules have more mass. It's going to be harder for them to vibrate. And so the speed of that wave is going to be considerably less. What's maybe not quite so obvious is that light's going to do the same thing. So this expression right here is for in a vacuum. So this is space-time. This is what happens when I have nothing else, no medium at all. However, if I am moving through some other substance, then what's going to happen is that the light ray is going to slow down. It's going to get small. It's going to take a little bit longer for it to go through. So the speed of light in a vacuum, if you use that equation, works out to be 2.998 times 10 to the 8th meters per second. It's the fastest speed in the universe. Nothing can go faster than that, because that's the speed of light in no medium. So any other medium that you put in there is going to be thicker than a vacuum. And so it's going to slow down that light wave. So in Pyrex glass, which is the kind that's often used in chemistry labs, it's a nice resilient kind of glass. The speed of light is only 2.033 times 10 to the 8th meters per second. So light slows down when it moves through that. And that's going to be true for any kind of substance that's not a vacuum. If it's a vacuum, then it's going to be as fast as it can possibly go. But if I put any other denser medium, and everything is denser than vacuum, light's going to slow down there. So rather than talking about the speed in that each medium, because that's a lot of numbers and it's not something that's really obvious for us, we define something called the index of refraction. So let's zoom in on that here. So we define the index of refraction to be the ratio of the two velocities. So you see we have ns here is going to be the speed of light in a vacuum divided by the speed of light in that medium, whatever that happens to be. So take a look at the next microtask here. Can the index of refraction of a material ever be less than 1? Pause the video and think about that. What would I need in order to get an index of refraction to be less than 1? Well, the only way to get that fraction to be less than 1 would be for the speed of light in the medium to be greater than the speed of light in a vacuum. But as we said, nothing can go faster than the speed of light in a vacuum. So that is not possible. So the index of refraction must always be greater than 1. So if you're doing some of these problems and you get an index of refraction that's greater than 1, or you get one that's negative, you got a problem. So something's wrong with what you've got worked out. So what is the index of refraction of light in a vacuum? What's the speed of light in the medium, in this case, a vacuum? Well, in that case, N is going to be C divided by C, which is exactly 1.00000, as many zeros as you want to have in there. So the index of refraction of the vacuum is 1. That's our comparison. Now, pause the video, pull out your calculator, see if you can very quickly figure out the index of refraction of Pyrex glass. Pause the video, do that now. Got it? Okay, so we know that N is going to be the speed of light, which is 2.998 times 10 to the 8th meters per second. And we're going to divide that by 2.033 times 10 to the 8th meters per second. And when you do that, you should get something in the neighborhood of 1.474. What are the units of the index of refraction? Well, to find the units, remember, we just take any equation, we work out what the units of that equation are, but meters per second here cancels. So the index of refraction has no units. It's strictly a ratio. It has no units at all. All right, let's zoom out here and let's see how we can apply this. So suppose we have a ray of light. And remember, it's not a ray. It's a line perpendicular to the center of the wavefront. And it's shining on this Pyrex glass. Let's zoom in for just a minute so that we can see it. So here's my ray. Now, if it were a mirror, obviously it's going to reflect off. And what we're going to learn later is always some of it's going to be reflected. But we're going to ignore that part for just now. We're just going to talk about the stuff that's actually coming into the glass. So out here in air, if this were in vacuum, it would be exactly 1.0000. Now, in air, it's about 1.0003. So air is actually just a little bit more dense than a vacuum. So most of the time, to the limit that we can do 4 significant digits, air is going to have an index of refraction of 1.000. So that's an important thing to keep in mind. If we tell you something's in air, you can assume that n is 1. Now, it's not quite true, is it? Because technically, air is more dense than vacuum. But to the 4 significant digits that we're working with here, it's fine. It's going to be 1.00. Okay, so let's look at some of the questions that we have here then. Which end of the incoming light ray will hit, or the wavefront, will hit the Pyrex surface first? And this is similar to what we did before. So right, the left end is going to hit first. This end right here is going to hit the surface. Okay, what will happen to the speed of the wavefront that is inside the Pyrex? Now remember, what's happening here is it's not bouncing off. It's going to be moving into this like this. And we're going to find, though, that it's not going to be at that straight line. So as soon as this wave comes in and it hits here, what's going to happen to the speed of the part of the wave that's inside the Pyrex? So let's say that we've moved in just a little bit. So what happens to the speed here of this part compared to the speed here for this part? Well, the speed of light is going to be slower, right? So that means it has to decrease. So here you've got an interesting situation. This side of the wave is moving slower than this side. How does the speed of the other end, that's this end, how does the speed of that end compare to the speed of this end? Well, the left side is moving more slowly than the right side. Let's see if we can imagine that. The wave is coming in, it comes into the Pyrex. This part down on the bottom here is now moving more slowly than this part on the top. So what effect does that have on us? I've always thought that this is a good way to envision it. So let's say that you've got a barrel that's rolling down a concrete slope onto grass. So it's coming in at this angle here, and then it hits the grass. Well, when it's rolling on the concrete, it can roll fairly quickly. When it hits the grass, it's going to slow down. But this end here hit the grass first, so it slowed down. So for just a little while, until the entire barrel is inside the grass, the left end is going to be moving more slowly than the right end. And so that means that it's going to curve just a little bit. It's going to turn because this end is not moving as fast as this end. And so that gives me kind of a bent path. So I move this way and then I move this way for that barrel. Well, the same thing is happening with light. So what happens, let's move this where we can see it. So for Pyrex then, it's going to look something like this. So I've got this light ray that comes in like this, but this end, as soon as it touches, it starts moving more slowly. But this end is still moving more quickly. So overall, the light wave has to stay perpendicular. So I'm not going to get any bends or anything like that. That's some people might think, oh, well, then my incoming wavefront, then my incoming wavefront must look like this. But remember that it always has to be perpendicular. The whole wavefront has to be perpendicular. So the only thing that can happen then is instead of having it like this, it must go something like this. Now, once the entire wave is in, then it can keep moving in its straight line. So it's only there at the interface that we're going to get any of that bending of light. So pause the video, kind of go back through that and make sure that you get it, because this is going to be a key thing. And if you understand how that process works, the rest of this is going to be a lot easier for you. So it comes in, this edge that hits first is going to slow down, but since it still has to stay a straight line, then this end, the part that's out, is going to go faster than the part that's in. And then once the whole wave is inside the material, well, then of course, it's going to keep going straight. All right. So let's see what we can figure out. Let's see if we can come up with a mathematical relationship for that. So we call this process refraction. Refraction literally means bending. And so anytime I have refraction of light, the light is bending. Now, the light wave, the wavefronts themselves are not bending. Remember, they've got to stay straight. They're changing direction. But the path of my incoming wave, which remember, this is just nothing more than showing you how those wavefronts are going, that path does bend from that. And so when we talk about bending of light, that's what we're talking about. Is we're talking about the bending of that kind of ray, that path marker that's coming in here. So we have an incident angle. And if I'm going to redraw my surface here. So here's my Pyrex. And then here's my normal. So we're going to call this the incident angle. Remember, we're going to measure that from the normal. And then this is going to get bent like this. We're not going to come out of the surface, out of the material just yet. And so this then is going to be my refracted angle. So R here means refracted as opposed to reflected. But either way, we're still going to measure it from the normal here, just like we talked about we were going to do with reflection. Okay, so let's see if we can come up with some mathematical expression for showing how much it bends. So we want to find a relationship between the incident angle and the refracted angle. So to build there, how is the frequency of light on the vacuum side related to its wavelength? What is the expression that relates the frequency to the wavelength out here in the incident material? We'll use the Fi for that. We should go through your notes, but you may remember that. That's just going to be C over lambda I. And that's a lambda there. How is the frequency of light on the Pyrex side related to its wavelength? That's going to be the same thing, right? So here, this is in the refracted medium, but now it's going to be a little bit different. Now it's got to be the velocity of the material. So divided by lambda R, right? Make sure that makes sense. Remember that we've made a big deal out of the fact that constant proportionality is the speed of the wave. However, the speed of the wave inside the Pyrex has changed because it's got a different index of refraction here. Now, the frequency of the light can't change. Let's think about why. Why can't the frequency of light change? We have another expression that relates the frequency to something else. Do you remember what that is? That's going to be the Einstein-Planck relation. So we know that F, we wrote it in terms of E, so let's do it that way. We know that the energy of the wave is directly proportional to the frequency, and it depends upon this constant that doesn't change. Well, by conservation of energy, I can't be losing any energy just because I moved into this different wave, this different material here. It's still an electromagnetic wave. It's still got all the same energy. There's no friction or anything like that. So the frequency of the light can't change because the energy can't change, right? So what property changes when the speed of light changes? If the frequency can't, you only got one other choice, then that's going to be the wavelength, right? So my wavelength, lambda, can change, and that's because E equals HF, and I have conservation of energy with this. Okay, so what we want to do now is we want to put all of this together so that I get an expression that relates the wavelength of light in Pyrex to the wavelength of light in vacuum in terms of the index of refraction of the vacuum, or of the Pyrex. All right. So we know that these two, let's see if we can build this together. We know that this frequency and this frequency have to be the same. It can't change. So I know that Fi is equal to Fr. So that means that this fraction must be equal to this fraction. So let's set them equal to each other. So I get C over lambda I must equal, we'll just say V since we only have one thing going on here, over lambda R. Now we want this in terms of the index of refraction. N for the material, for our refracted material, is just going to be, C over V. Right? So let's see if we can manipulate this expression to give me C over V. Let's do that. So if I divide through by a V on both sides, I get lambda IV, 1 over lambda R. Let's multiply my lambda I up here, and that gives me C over V equals lambda I over lambda R, and that, of course, is equal to N. So that's NR. So the ratio of my wavelengths is also going to be my index of refraction. And that kind of makes sense if you think about it. If the wavelength is changing in proportion to the velocity, then sure, that makes a lot of sense. Okay, so we're going to solve this then for our refracted wavelength here, since that's what we're usually interested in. So I'm going to multiply both sides by lambda R, and that gives me lambda I equals lambda R over NR, but I want the lambda R by itself, so I'm going to divide both sides by NR. And so finally I get lambda R is going to be equal to lambda I divided by that index of refraction. So that is how much that the light ray will bend if it goes from vacuum, or air in our case, into our new medium. Okay. All right. Next question says, suppose the ray isn't traveling through vacuum, but instead is traveling through water, just as an example, which has an index of refraction of 1.33. So now what we want you to do is come up with a mathematical expression for the relationship between the wavelength in water to the wavelength in the Pyrex. And you've got everything set up here. The only difference is that the speed of light is now going to be C. And so you're going to have to work out how I can relate that to my index of refraction. Pause the video and see if you can do it. This is an important skill that if you can do this, then you're in pretty good shape for this section. Pause the video. You got it? Make sure you really got it. Okay, so we know that F1, which we will call our frequency coming from the water, it must be traveling at the speed in the water, which we'll call V1, and it's going to have some wavelength. Once it gets in the Pyrex, it's going to have F2, and that's going to be V2 over lambda 2. Now again, F1 is equal to F2, and so that tells me that V1 over lambda 1 must equal V2 over lambda 2. Remember that I want this in terms of the index of refraction. So I'm going to take my expression right here, and I'm going to use that. I'm going to solve this for V. So let me do this over to the side. If I have N is C over V, then V must be C over N, like that. Okay, so we will put that in for this expression here. Let me scroll this up just a little bit. And I will get C over N1, lambda 1, is equal to C over N2, lambda 2. Now, I can invert this. I want to get rid of these C's, right? And so I can get 1 over N1, lambda 1, is equal to 1 over N2, lambda 2. But that's a little bit weird, but we can obviously just invert everything. And so here is our relationship between the wavelengths for any media. And so you see that we're getting the same thing that we would have gotten up here. It's just that I haven't multiplied through by the N1. So let's solve for the wavelength in Pyrex. So I want to get the lambda 2 by itself so that it matches this form that I have here. All I need to do then is I can say that lambda 2, which is in my refracted medium, must equal, divide both sides by N2, N1 over my refracted one times my incident right here, which was 1. 1 was my incident and 2 was my refracted. So this is a more general expression for this. And this also holds even if I'm in vacuum. Remember, if I'm in vacuum, then Ni is simply 1. And so I'm going to get exactly the same thing. So this is my general expression for relating the wavelength to the ratio of my indices of refraction. All right, now that we know that our light wave is bending, let's see if we can figure out how much it's bending. And so we're going to look at two critical cases here. We're going to look at this case right here, where the left edge has just touched the Pyrex. And then we're going to look at this case here, where the right edge has just gotten completely into the Pyrex. And those are the two cases that matter. If you think about it in terms of our barrel that was rolling, as long as we were completely on the concrete, the barrel was moving straight. Once we were completely in the grass, the barrel was moving straight. So the change here, the turn, is going to occur in between these two extremes. And to figure this out, we're going to have to be really careful and watch our geometry. We're going to just step through some angles here. So first step is we need to figure out what is the value of this angle BAE, that angle right there. All right. So we are interested in this angle right there. All right, so to start off with, if this angle is theta I, what is the angle B up here? So this is a right angle. If this is theta I, then this must be 90 minus theta I, because it's a right triangle. All right, now using that, so we know that this angle is 90 minus theta I. What then must be this angle that we're actually interested in, this one right here? Here's my triangle now that I'm going to look at. This is a right angle because it's perpendicular. So this one must be 90 minus theta I, or just theta I. So that angle is theta I. If you don't follow that, go step back through the triangles and let's make sure that you do. Okay. So let's look at the other triangle. We want to find the value of EDF. EDF is this angle right here. And that's going to be pretty small. So let's blow it up and let's make it a little bit bigger here. So we're going to look at this triangle to start off with. Like so. Now this angle is theta R. That's my refracted angle that's coming in. So what must this angle be, which is this tiny little angle right in there? Well, this is perpendicular, right? So that's a right angle, so that must be 90 minus theta R. All right. So this tiny little angle here is theta R. So let's look at this That is 90 minus theta r. So let's look at this angle here. This is another right triangle. So let's make it big again. So we decided that this angle was 90 minus theta r. So what must this angle be, which is the angle we're interested in? That must be theta r, right? So you see how we can get that. All right, so now let's compare those to the sides that we have. The distance BD must be equal to one wavelength in the first medium, right? Because of my wave propagation. So by the time I come through here, that's going to be one wavelength. And this must be, similarly, the distance AC must be equal to the wavelength in the second medium. So we want to write a mathematical expression for lambda 1, this one right here, in terms of the side AD, which is right here. Let me do that in red so that we can see it. In terms of this side. So we want to do this in terms of this. And the incident angle, theta I. Now we've decided, don't be fooled here. This, yes, this is the incident angle, but the whole reason we found this BAE, this angle right here, we found that that angle is also theta I. And that makes it a little bit easier to do this triangle. So if this is theta I, and I want to do it in terms of BD and AD, which trig function do I want to use? That's going to be the sine. So that tells us that sine of theta I must equal the opposite BD over my adjacent, which is AD. However, BD is actually the wavelength. So that's our incoming wavelength, our incident wavelength. Now, yes, we've still got this AD, which is arbitrary, so our goal is we're going to have to get rid of that at some point. All right, so now we want a mathematical expression for lambda 2, so the wavelength in this medium over here. And we're going to do the same thing. Scroll up just a little bit. So now we want it in terms of, I'll go to red, we want it here and here. Okay. Now we decided that this angle EDF here, we decided that that was theta r. So that angle right there is theta r, and this angle must be a right angle. So what can I say? How can I write that then? This in terms of AD, which trig function am I going to use? Well, it's going to be the sine again. And so I get sine of theta r must equal AC over AD. And so that's going to be lambda 2 over AD. All right, so now we've got what we need. So we're going to solve these expressions for AD and set them equal to each other. That way we can get rid of AD. So let's solve this first one. So we have sine of theta I is equal to lambda I over AD. So that tells us that AD must be equal to, it's lambda I over sine theta I. And similar, we have that sine theta r is equal to lambda 2 over AD. And that tells us that AD must equal lambda 2 divided by sine theta r. Let's scroll up a bit more so we can work here. Okay, so those need to be set equal to each other. These two right here needs to be set equal to each other. So lambda I over sine theta I must equal lambda 2 over sine theta r. And we can rewrite this a little bit more neatly. This then, if I multiply both sides by sine theta r and both sides by sine theta I, then I get lambda 1 times sine theta I, sine theta r must equal lambda 2 times sine theta I. Right there. So this expression is called Snell's law. And just as a side note, you'll see this in most physics textbooks as written this way with two L's, particularly most American textbooks. Snell lived in the 1600s, and we only have a few documents where he actually signed his own name. And in most of those, and most of the ones that were written by him himself, he seems to have spelled his name this way with one L. So that's the convention that we'll stick with here. That's opposite from what you're going to see pretty much everywhere else. But we want to be respectful of how he probably spelled his name himself. So that's the way we'll be spelling Snell's law. Just remember that if you're searching on the internet or whatever, you're going to see two L's for there most of the time. Okay, so let's look at the next page here. Let's scroll down to where we can see it. So we want to use the relationship between the wavelength and the index of refraction to rewrite Snell's law in terms of indices of refraction, because most of the time that's what we're interested in. We're not really going to be able to measure what the wavelength of light in the material is. We may know what we sent out, but we probably aren't going to know what came in. But we are going to know what the index of refraction of that material is, because we can look that up. So let's start out with writing down lambda 1 is sine theta r equals, or times sine theta r equals lambda 2 times sine theta I1. And let's see if you can do this yourself. So pause the video. We want to use the relationship between the wavelength and the index of refraction. And remember that we found that lambda 1 must equal lambda 2 divided by n2 over n1, just like that. So use this expression and let's see if you can get rid of the lambdas. It's going to be pretty straightforward. Pause the video and make that happen. Okay, all we need to do is just substitute in for lambda 1. And so we get lambda 2 n2 over n1 sine theta r must equal lambda 2 sine theta I. And now my lambda 2's are going to cancel. I'm left with n2 over n1 sine theta r must equal sine theta I. And just to make it pretty, I'm going to multiply both sides by n1. I get n2 sine theta r must equal n1 sine theta I. And this form is a little bit easier to remember because what this says is that the angle of incidence, we're in the medium n1 times, so n1 times that sine theta I is going to equal our refracted angle, the sine of that, times our medium that we're actually refracting in. So in this form, you see that it's opposite. So I've got my refracted angle, but then this is my wavelength outside of the material. So this is my angle inside the material. This is my angle outside the material, my wavelength inside. Well, that's pretty confusing. So why not do it this way? And so this is the form of Snell's law that you're going to use most of the time. Most of the time, we're going to have this in terms of my index of refraction. Okay. All right. So now once we know that, there is an interesting case that we can do where we can find something called total internal reflection. And what you'll find is that if I have a material and I've got light inside a more dense material, there's going to be a case where if I have light coming this way and trying to get out, it's going to get refracted away from my normal, right? Because I'm moving, this might be n equals 1. Let's say that's air. And this might be Pyrex, or more fun, it could be diamond. Then it's going to get refracted away. So remember, it's always going to be smaller inside here. There's going to be an angle at which, when I come in here, it's going to be trapped inside. And that's called total internal reflection, which is terribly misnamed because it has nothing to do with reflection. It's refraction that's coming into play here. So diamonds sparkle because they've chosen the facets in such a way that when the light hits off the different facets, it stays trapped inside the diamond. And then, of course, there's going to be some small variation, so it bounces around a whole lot and then eventually escapes. But if you look at it from a different angle, you're looking at a different part of the light. And so this is what's going to make it sparkle. Fiber optic cables have the same thing. They've got a cladding that has a lower index of refraction around their transparent core. So the light always stays inside that cable, even if I bend it, because we've got total internal reflection going on. All right, so let's see if we can do that. take a look at the scenario here, and we want to figure out the critical angle that will give me total internal reflection. And so that's the angle that you want to cut the facets of your gemstone in. So our scenario then is, here we've got a block of diamond. The index of refraction is about 2.42. And we're going to be in air, which we can use to be 1 to 3 significant digits, certainly. Or you can go ahead and carry it out to 5 if you really have to. But remember, you're only going to keep 3 at the end. So how are we going to get where we need to be? Okay, so we're simply going to use Snell's law. But we want the angle of refraction to equal 90 degrees. So that my angle here is going to be 90 degrees. So this is going to be my incoming angle. That's going to be my critical angle. And then my outgoing angle is going to be 90 degrees. So let's write down what we know. We know that our refracted angle has to equal 90 degrees. We know that the index in air, that's going to be N1, is going to be 1.003, and N2 in our material is going to be 2.42. And what we want to find is our critical angle, which is our angle of incidence. And we're going to find that in degrees. And then, of course, our only equation is going to be Snell's law. So we'll have N2 sine theta C, in this case, is going to equal N1 sine theta R. And you can use the next page for working this out, but I'll just do it over to the side here. So all I need to do is work out solve for this sine theta C. So N2 sine, let's just copy it down here, sine theta C is going to equal N1 sine theta R. So sine theta C must equal N1 over N2 sine theta R. And so theta C is going to be the inverse sine of N1 over N2 sine theta R. Just like that. Okay. So plugging in numbers here, it's going to be the inverse sine of N1 we decided was 1.0003, and N2 was 2.42, and my sine of my angle is going to be 90 degrees. That's going to be my condition for total internal reflection. And if you punch that into your calculator, work it out, you're going to get 24.4 degrees. So that's the angle you need to cut your facets in order to make sure that you have total internal reflection all the way around. Now, take one last look at this page here. There's a question down at the bottom. It says, is it possible to get total internal reflection when the light moves from a lower index of refraction to a higher index of refraction? So say we're coming from air into the diamond. Can I get total internal reflection? And no, that's not possible, because that would, if you take a look at our fraction here, this would have to be greater than 1, right? If I'm going from 2.42, because N1, remember, was what my exit was. Let's draw our material here. So now I've got this coming in this way, and I want it to get bent. So what I was calling N1 here is now going to be N2. So this is going to be 2.42. This is going to be 1.003. And then if that number is greater than 1, well, then the inverse sine is undefined. So no, there's no way that that's going to be able to work. And think about how that is. So what you need then is you need to have this material that's going, the light coming from inside to outside. That will give you total internal reflection, but you will never get total internal reflection coming from outside, so from air, lower index of refraction, to inside. Okay, so now we've got the basics for reflection and refraction. We can calculate an angle. If I have a mirror, I can calculate that angle that's outgoing, and they're just going to be the same. That one's usually pretty easy to figure out. The refraction is a little bit more complicated, but basically Snell's law is going to tell you everything that you need. If I know my incoming wave, I can figure out what that angle for the outgoing wave is, and it's just a matter of keeping up with your indices of refraction. We also talked about total internal reflection, which is not reflection at all. It's simply refraction where it stays inside the more dense medium. What we're going to do next is now we're going to start seeing how we can apply that. And one of the main ways that we're going to do that is through the use of lenses and mirrors. Using lenses and mirrors is one of the main ways that we make eyeglasses and telescopes, and the focusing beam on your DVD or Blu-ray player. Pretty much everything revolves around this idea of using lenses and mirrors. So it's a really important concept, but it all comes back to just using that law of reflection and Snell's law. We'll see you then.